Welcome! In today's session, we'll be tackling LeetCode problem number 1118, number of days in a month. This is a straightforward yet fundamental problem that asks us to determine the number of days in a given month and year, while accounting for leap years. Let's dive in and explore the approaches to solve this problem effectively. In this problem, we are tasked with determining the number of days in a given month for a specific year. The challenge lies in correctly accounting for leap years when calculating the days in February. The input is structured as two integers, the year, which ranges from 1 to 10,000, and the month, which will always be a valid month from 1 to 12. For the output, the function is expected to return a single integer representing the number of days in the specified month for that year. Let's explore some examples to understand this better. In the first example, the input is the year 1992 and the month of February, represented as 2. The output is 29. This is because 1992 is a leap year. It meets the conditions for a leap year as it is divisible by 4 and not divisible by 100. In leap years, February has 29 days, so the returned value is correct. Another example is the year 2000, also for February. Here, the output is again 29. The year 2000 is a leap year because it is divisible by 4 and additionally divisible by 400. Therefore, February in this case also has 29 days. Now, consider the year 1900 with the month of February. The output here is 28. While 1900 is divisible by 4, it fails the leap year condition because it is divisible by 100 but not by 400. This makes it a non-leap year, and February in such cases has only 28 days. Another example is the year 2023 with the month of July, represented as 7. Here, the output is 31. July is one of the months that consistently has 31 days, regardless of whether the year is a leap year or not. Looking at the constraints for this problem, the year will always be a positive integer within the range of 1 to 10,000, and the month will always be a valid value between 1 and 12. The problem requires careful handling of edge cases, such as the smallest possible inputs year 1, month 1, which corresponds to January with 31 days, and the largest possible inputs year 10,000, month 12, which corresponds to December with 31 days. Additionally, February must be correctly calculated for both leap years, like the year 2000, and non-leap years, like the year 1900. The behavior of months with 30 days, like September, also needs to be accounted for. To solve this problem, it is crucial to understand the leap year rules. A year qualifies as a leap year if it is divisible by 4 but not divisible by 100, unless it is also divisible by 400. February has 29 days in leap years and 28 days otherwise. The rest of the months have fixed numbers of days. January, March, May, July, August, October, and December always have 31 days, while April, June, September, and November always have 30 days. With this clear understanding of the rules and edge cases, we can confidently implement the function to handle all possible inputs and scenarios. To solve the problem of determining the number of days in a given month for a specific year, we need to account for both fixed month lengths and the variability of February in leap years. One approach is the brute force method, which involves using a hard-coded mapping of months to their respective days. For instance, most months have a consistent number of days, either 30 or 31, except February, which requires checking if the year is a leap year to decide between 28 or 29 days. This approach is highly efficient in terms of both time and space complexity, with direct lookups and simple conditional logic making it an O-1 operation. Its simplicity and ease of implementation are significant advantages, though it does rely on hard-coded data, which might be less flexible in handling certain edge cases. Nonetheless, it's a straightforward and effective solution for this problem. Another possible approach is based on mathematical logic. Instead of storing the number of days for each month explicitly, we use mathematical calculations to derive the days. For February, we use leap year criteria, and for other months, we rely on their modular relationships to determine whether they have 30 or 31 days. This method eliminates the need for hard-coded values, making it more dynamic. Its time and space complexity remain O1, as the calculations are constant time operations that don't require additional storage. While this approach avoids hard-coding, it introduces slightly more complex calculations, which may increase the likelihood of implementation errors. Alternatively, we could leverage a calendar library, such as Python's calendar module, to fetch the number of days directly using pre-built functions like calendar.monthRange. This significantly simplifies the implementation, as the library handles all internal logic. However, it introduces a dependency on external libraries, which may not be feasible in restricted environments. Both methods offer different trade-offs in terms of complexity and flexibility. For this problem, we've chosen the brute force approach as our strategy. It's particularly well suited for this scenario due to the fixed input domain. There are only 12 months, and their day counts are consistent, except for February. Leap year calculations, which determine February's day count, are computationally inexpensive and involve just a few modulo operations. The simplicity of this approach ensures it's intuitive and less prone to errors, making it easier to implement and debug. Unlike the mathematical approach, it avoids the need for complex calculations, and unlike the library-based approach, it doesn't rely on external dependencies, ensuring portability. Overall, the brute force method offers a straightforward and efficient solution that aligns well with the problem's constraints. Every approach comes with trade-offs. While the brute force method is straightforward and easy to debug, it doesn't have the elegance of deriving results purely from mathematical logic, as seen in the mathematical approach. On the other hand, compared to the calendar library method, it avoids reliance on external tools, making it more portable and adaptable to different environments. In conclusion, the brute force approach strikes the best balance between simplicity, efficiency, and maintainability for this problem. It addresses all requirements effectively while minimizing complexity, making it a practical and reliable choice. To solve the problem of determining the number of days in a given month for a specified year, we start by clearly defining the input and output. The input consists of two integers, the month, which ranges from 1 to 12 to represent January through December, and the year, which can be any valid year from the Gregorian calendar. The output is a single integer that represents the number of days in the specified month and year. Next, we need to establish a base mapping for the number of days in each month. Most months have a fixed number of days, 31 days in months like January and March, while months like April and June have 30 days. February, however, varies between 28 and 29 days depending on whether the year is a leap year. This base mapping is represented using a dictionary, days_an_month, which allows us to efficiently store and access the number of days for each month, ignoring leap year adjustments for now. Now, we address the special case for February by determining if the given year is a leap year. Leap years follow a specific pattern. A year is a leap year if it is divisible by 4, but years divisible by 100 are exceptions unless they are also divisible by 400. For example, 2000 is a leap year because it is divisible by 400, but 1900 is not because it is only divisible by 100. To encapsulate this logic, we define a helper function as _leap_year that takes a year as input and returns a boolean indicating whether the year is a leap year. Once we have this function, we can adjust February's days accordingly. If the month is February and the year is a leap year, we override the default value of 28 days and return 29 days for February. This ensures that the algorithm correctly accounts for leap years and handles February's variable length. After handling February's special case, we can now return the number of days for all other months. For months other than February, we simply use the days_an_month dictionary to look up the predefined value for the given month. This allows us to return the correct number of days in constant time. To summarize, the leap year calculation ensures the algorithm accurately adjusts February's days every 4 years while adhering to the Gregorian calendar rules. The dictionary-based lookup guarantees efficient access to the fixed days for other months. Additionally, it's important to consider edge cases, such as February in a leap year versus a non-leap year. For instance, February 2000 should return 29 days, while February 2023 should return 28 days. This ensures our algorithm is robust and handles a wide variety of inputs correctly. In addition to February, we should validate the correctness of other months, such as April and June, which have fixed days. While the algorithm does not explicitly handle invalid inputs, such as a month value outside the range of 1 to 12, this could be addressed with additional input validation. The algorithm relies on two key data structures. First, the days_an_month dictionary stores the number of days for each month and enables constant time lookups, Second, the is_leap_year function encapsulates the leap year logic, making the code modular and reusable. From a complexity perspective, the algorithm is highly efficient. The time complexity is 1, because determining whether a year is a leap year involves a fixed number of arithmetic operations, and looking up the number of days for a month in the dictionary is also a constant time operation. The space complexity is also 1, since the dictionary and helper function require a fixed amount of memory regardless of the input. This makes the solution both scalable and performant. Finally, let's look at the complete implementation of the algorithm. The number_of_days function begins by defining the days_an_month dictionary, which stores the default number of days for each month. It then defines the helper function is_leap_year, which encapsulates the logic for determining whether a given year is a leap year. Next, the function checks if the given month is February. If it is and the year is a leap year, it returns 29 days. Otherwise, it returns the predefined value for the given month from the dictionary. This implementation is concise and ensures correctness by leveraging the dictionary for efficient lookups and the helper function for modular leap year checks. With this approach, the algorithm handles both typical and edge cases effectively, providing the correct number of days for any valid month and year combination. This Python solution implements the number of days function, which takes two inputs, year and month. The goal is to determine the number of days in a specific month for a given year. The function first defines a list days_in_month containing the standard number of days for each month, from January to December. For all months except February, these values remain constant. However, February's number of days depends on whether the year is a leap year. To determine if a year is a leap year, the function uses the following rules. A year is a leap year if it is divisible by 4 and not divisible by 100, or if it is divisible by 400. This accounts for exceptions like the year 1900, not a leap year, and the year 2000, a leap year. If the month is February, month equals 2, the function checks the leap year condition. If the year is a leap year, February has 29 days, otherwise, it has 28 days. For all other months, the function refers to the days_in_month list and returns the corresponding value for the given month, adjusting for zero-based indexing by subtracting 1. This implementation is efficient, with a constant 1 time complexity, as it involves a few conditional checks and a direct lookup in the days_in_month list. The solution handles all edge cases, including years that are divisible by 100 but not 400, and correctly calculates days for all months of any valid Gregorian calendar year. This is the Java implementation of LeetCode problem number 1118, number of days in a month. The solution mirrors the Python logic, converting it to Java syntax. The main differences include explicit type declarations for method parameters and using an array to store the number of days in each month for non-leap years. The leap year check follows the same logic, using modular arithmetic to determine if a year is divisible by 4 but not by 100, or divisible by 400. The implementation is concise and adheres to Java conventions. To solve this problem, let's start by considering a non-leap year scenario with February as the input month. For example, the year is 2023 and the month is February, represented as year equals 2023 and month equals 2. First, we initialize a list called days_in_month that contains the number of days in each month of a non-leap year. February is represented as having 28 days in this list, which will be adjusted later if the year is determined to be a leap year. Next, we check if the input month is February by evaluating whether month equals 2. Since this condition is true, we proceed to determine if the year 2023 is a leap year. For a year to be classified as a leap year, it must either be divisible by 4 and not divisible by 100, or it must be divisible by 400. In this case, 2023 is not divisible by 4, meaning it does not meet the criteria for a leap year. As a result, February in 2023 has 28 days, which we return as the final output. Now, let's consider a leap year scenario, specifically with the year 2020 and the month of February. The input parameters are year equals 2020 and month equals 2. Again, we initialize the same days_in_month list as before. Since the input month is February, we need to evaluate if 2020 is a leap year. This time, the year 2020 satisfies the leap year conditions because it is divisible by 4 and not divisible by 100. Therefore, 2020 is a leap year, and February in a leap year has 29 days. We return 29 as the final output. Lastly, let's look at an example where the month is not February. For instance, with year equals 2021 and month equals 7, July, we initialize the days_in_month list as usual. Since the input month is not February, there's no need to check for leap year conditions. Instead, we directly retrieve the number of days for July from the list. Using zero-based indexing, days_in_month, 7 to 1, gives us 31, which is returned as the final output. In this solution, we're calculating the number of days in a specific month of a given year. To start, we initialize the days_in_month list, which contains 12 integers, one for each month of the year. Since this list always has the same fixed size, 12 elements, its initialization is a constant time operation, or O1. Next, we handle a specific case for February, which might have 28 or 29 days depending on whether the year is a leap year. Checking for a leap year involves evaluating three conditions: whether the year is divisible by 4, not divisible by 100, or divisible by 400. Each of these checks is performed using simple arithmetic and logical operations, making each individual check an O1 operation. Combining these conditions doesn't change the complexity, so the entire leap year check remains O1. When the input month is not February, the solution simply retrieves the value from the days_in_month list using the index month 1. This direct index lookup in a list is a constant time operation, or O1. Since every step in our solution, initializing the list, checking for a leap year, and performing a direct lookup is O1, the total time complexity of the function is O1. Now, turning to space complexity, the days_in_month list requires memory for 12 integers. As this list is of fixed size, its space usage is constant, or O1. The input parameters, year and month, are just two integers and also require constant space, which means their contribution is O1. No additional data structures are created, and all intermediate calculations, such as modulo operations or comparisons, use constant space. Therefore, the space complexity of the solution is O1. This efficient use of memory establishes that the overall space complexity of the solution is O1. Now, when we compare this approach to a naive or brute force solution, the advantages become clear. For example, a brute force method might involve iterating through all days of a year or month to count the total number of days. To determine whether February has 28 or 29 days, a brute force solution might count leap years from year 0 to the input year, which would take O(n) time, where n is the input year. Similarly, iterating through all months to calculate their days would add unnecessary complexity. In contrast, our solution avoids these inefficiencies entirely by using arithmetic operations and direct lookups, achieving optimal performance. To conclude, our mathematical proof reinforces that each operation in the function is O1, with no loops or recursive calls, making the overall time complexity O1. Additionally, since there is no dynamic memory allocation or growth based on input size, the space complexity remains O1. When solving the problem of determining the number of days in a month, there are some common mistakes to be aware of. First, ignoring leap year rules for February is a frequent error. Leap years occur under very specific conditions: if the year is divisible by 4 but not by 100, unless it is also divisible by 400. For example, the year 1900 is not a leap year, but 2000 is. Failing to account for this can lead to incorrect results. Another issue is hard-coding the number of days for each month. While this might seem simple, it's error-prone and not easily maintainable. Instead, consider using a data structure like an array or dictionary to store these values. Out-of-bounds errors are another pitfall. If you're working with an array, it's important to validate that the input month falls within the range of 1 to 12. Neglecting this step can cause runtime errors, especially with invalid inputs. Additionally, edge cases such as months outside the valid range or negative years are often overlooked, leading to incorrect or incomplete solutions. Lastly, overcomplicating the code with long if-else chains for each month can make the solution harder to debug and maintain. A simpler, structured approach is usually more effective. To perform well in interviews, it's essential to focus on certain key aspects of your solution. First, strive for reusability by using a structured approach, such as storing the days of each month in an array or dictionary. This not only keeps your code clean but also makes it easier to extend or modify later. Understanding and explaining leap year rules is another critical area. Interviewers often ask follow-up questions to make sure you can handle leap year calculations correctly, so be prepared to articulate the logic clearly. Input validation is also crucial. Make sure your code can handle edge cases like invalid months or negative years. This demonstrates your attention to detail and ability to write robust solutions. Finally, prioritize clarity over cleverness. While it might be tempting to write overly complex or compact code, interviewers value solutions that are clear, concise, and easy to understand. Use intuitive variable names and include comments to make your thought process evident. This problem is also connected to several other LeetCode challenges that test similar skills. For instance, LeetCode 190, Reverse Bits, emphasizes the importance of handling edge cases, which is a key aspect when validating month and year inputs. Similarly, LeetCode 202, Happy Number, focuses on number manipulation and iterative logic, which parallels how you might approach leap year calculations. LeetCode 13, Roman to Integer, highlights the importance of efficient mappings, much like how you map months to their respective days. Lastly, LeetCode 118, Pascal's Triangle, tests your ability to handle edge cases and construct structured solutions, which is directly applicable to ensuring your implementation is both robust and well organized. There are several alternative approaches to solving this problem, each with its own advantages and trade-offs. Using a dictionary to store the mapping of months to days is a great option for better readability and flexibility. While a dictionary may be slightly slower in lookup compared to an array, it's especially useful when handling non-sequential or customized inputs. Another approach is to hardcode month values using if-else conditions. This method might be intuitive for beginners, but it's verbose and harder to maintain, making it less suitable for larger or more complex problems. Lastly, you can improve modularity and readability by creating separate functions for tasks like leap year detection and day calculation. While this modular approach enhances reusability and structure, it can slightly increase the complexity of your code due to additional function calls. Depending on the context, choosing the right approach can help you balance clarity, efficiency, and maintainability. Great job tackling this problem. To recap, we covered how to calculate the number of days in a month while considering leap years. This problem emphasizes the importance of edge case handling and efficient logic. I hope this walkthrough was helpful. If you enjoyed it, don't forget to like, share, and subscribe for more coding solutions. Happy coding, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!